Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Today with problem 425 word squares. So we're doing another hard one. It's got a really good like to dislike ratio. Decent submission to acceptance rate. It looks like only Bloomberg has asked it recently, which is surprising because I think it's a really good question. So I wouldn't be surprised to see if there are other companies that pick it up in the months or years to come. But regardless, as always, I think it's a good one, and so that's why I wanted to walk through with you guys today. The instructions tell us that we're given a set of words without duplicates and that we need to find all word squares that we can build from them. And they give us kind of a fancy definition here of word squares where a sequence of words forms a valid word square if the kth row and column read the exact same string where k is between 0 and the maximum of the number of rows and columns. For example, the word sequence ball, area, lead, and lady forms a word square because each word reads the same both horizontally and vertically. Namely, column row 1 is ball, and if we read column 1, it's also ball. Area is row 2, column 2 is area. Lead is row 3, column 3 is lead. And we need to figure out how to build one of these or to build all the possible word squares given a list of words. In our notes, we're told that they're between 1 and 1,000 words. They all have the same length, all right, so that makes it easier. And the word length is at least 1 and at most 5. Each word contains only lowercase English alphabet. Cool. So running with the example we saw, area, lead, wall, lady, and ball. There are two ways to do it. Wall, area, lead, and lady. And ball, area, lead, and lady. And I'll kind of zoom in. You can see the first row reads like the first column. Second row reads like the second column. So on and so forth for both these examples. So we'd return both of these. And they give us another example here. Cool. So it's rated hard. I think it's a bit of a tricky problem. And yeah, let's think about how we're going to do this. When we're given a question like this that involves, how do I put it, that involves returning all the possible combinations of something, more often than not it will involve some form of backtracking. And usually I find a lot of people get freaked out when they hear that they got to do backtracking because it sounds like this complicated cool thing. Backtracking is really just the computer science way of saying trial and error, which can be even more colloquially referred to as throwing shit at the wall and seeing what sticks, which is exactly what we're going to do today and how we're going to solve this problem. The general approach with this backtracking stuff goes like this. Let me start. So any single one of these words hypothetically could start off a what do you call it, a word square. So maybe area is the first word, and from area we see is there what word can go next, and can we keep building a square from here? If we can, cool, we keep going. If not, all right, we're going to return and let's try the next word. So just even by default, we got to start by somehow looping through each one of these words and saying, okay, let me pick this word and let me start a square. The question becomes though, how do we define, what are the conditions for something actually being a valid square? If I started with area, right, I started with this word, so this first one here. What goes next? What can go next? Well, to answer that, let's think about the following. Let's look at an example that worked here. So I'll do this one here. Ball, area, lead, and lady. So we'll do ball, area, lead, and lady. All right. So there's one thing that I want to notice. Take a look at this square, and it is a square. I know it looks like a rectangle, but it's a square. And I want to notice one thing about it. So we understand it reads column-wise and row-wise the same, but let me kind of draw. Oops. Let me draw a diagonal line through here. So look at the diagonal of the square, right? And tell me what you see. Let's look at this top triangle over here. Looking at this top triangle, we can see that this is symmetrical, right? About the diagonal, we have the A and the A here. We have the L and the L here. We have the L and the L right over here. And so really, by looking at this part over here, I can almost start to determine what's going to be on the other side. And let me take that a step further. So what I'm going to do here to actually show you how we're specifically gonna figure out. Well, that's not what I wanted. Paint into layer. Maybe that's what I want. That's definitely not what I want. Alrighty. That didn't go too hot. Why don't I do this? Let me do it the old-fashioned way. I'm going to scratch these out. I'm sorry. Maybe we'll make it red. So I'm gonna scratch these. Oh, that's not red. Forget it. We're sticking with black, guys. If it ain't broke. So I'm gonna scratch these out. We'll ignore these for a second. Let's think about. Whoa. All right. I didn't even know what power I had here. Let's say use the word ball here. I'm gonna undo all this. I'm gonna start with the word ball. Right. So we know ball is gonna give us a bona fide answer. I'm gonna start with the word ball. Oops. B-A-L-L. How do I choose my next letter? So I'm one word into my word square. I'm one word in. And what does this next kind of column have to start with? Well, if we know that we need to read ball this way and this way, then the second word must start with an A, right? It must start with an A. So this is my word one. And my prefix, the prefix to this word must be an A. I don't know what the rest of it is going to be, but it must be an A. The reason it must be an A is because that would be our next step in reading this from top down and from left to right the same way. Knowing that my prefix must be an A, I can now walk through my array of words and say which one of these words begins with an A. It just so happens that we only have one candidate, and that candidate is area. So I say area will be my second word. Cool. I'm now two words in. So when I had one word, I was looking at this index. So one word in, index 1 for my prefix. Now, I'm looking for my next word. What is my next word going to have to look like? Well, it's definitely going to have to start with an L, because we're going to have to read this L, and we're going to have to read ball down this way. But if you remember the symmetry over here that I drew out, it's also going to actually need to have an E right over here. It's going to need this letter over here and this one right underneath it. So at index 2, we're two words in. Now we need all the letters in index 2 of all the words. So both of these. Our next word is going to have to start with LE so that we have this symmetry that will read, across the diagonal that we have. LE, so I determine, okay, the prefix I need is LE. So I'm going to jot that down, and I'm going to look at what candidates I have for the word, that start with LE. Well, in this case, it's only lead. Lead is my only candidate. So my third word must then be lead. I'm on to my next word. And again, you can ask yourself, what prefix would I need? So in order for this to be a word square, what does my next word need to begin with? We know it needs to begin with an L for sure, because again, ball. But remember, we also got area, so we're going to need an A here. And we also have lead, so we're going to need a D here, right? Lad. Where do we see this? Well, we see this in this third column over here. We're 3 words in. We need to go to column 3 and find all of the letters for the words we have so far sequentially and say these 3 letters form the prefix of the next word we need. That word is going to need to begin with LAD. I look for my words. Lady is the candidate. I will put in lady. Lady. And guess what? Since we now have each of these words is of length 4, and we've got 4 words in here, we must be done since it's a word square. Since I've gotten to this point, I can then say, awesome, I'm done. I'm going to add this to my result, and then let me backtrack and see if there are other solutions. Another way there could be solutions. Let's say that we had a bit of a spicier, spicier list of words, and one of those spicy words was, instead of lady, we also had lads. If we had lads, then after I backtrack, okay, so I've done this, I've returned my answer, and I take a step back, and what I'm going to be doing is I'm going to be keeping some sort of current list of these words that I've got here. I've got 3 of them so far. I had lady on there. I tried it. It worked. I'm going to pop it back off now, and I'm going to say, were there any other words that began with LAD? In this made-up example, sure, there was also lads, this word that I just added on. Again, I'm only doing this to extend the example. So I could have lads. Again, if I now have a 4x4 square, I can add that to my result, and we're done. And what backtracking means essentially is, let me try this word. Let me try all the candidate words that I had. At every step along the way, I was looking for candidates. When I found this prefix LAD, I was looking for all the candidates that I can possibly add into this part of the square. In the example we started with, it was only lady. In the one that I I kind of extended. We also had lads. So we would put on lady, we would do a recursive call, this backtracking call, and say, okay, cool, that ended up working out. All right, we tried with that, that's done, let's pop it back off. Is there any other candidate? If there is, let's try the next one. We work that one out, we pop it off, and we keep going. We would then actually kind of, so imagine literally backtracking. Now we tried lead, then we'd pop lead back off, and then we'd add on another word that began with LE if there was one, and so on and so forth. And I'm gonna put this back here so we have a working example. Thing I can't do anymore. Alrighty, awkward. And so that's how we do this. And I started with ball, but really there's also another solution. And that solution began with wall. So we could have also started, and we will try all these, and we're going to do this by looping through every one of these words. We could start with wall. If I start with wall, I understand that my next word must begin with all the letters and all the words at index 1. Which words begin with A? Well, again, there's only one here, so we're going to add area to our words. The next word we need is going to have to begin with LE for the same logic we had. We're going to have lead, and then again, you can I think you can walk through the example, and you can try this one out by hand to see if it'll kind of work for you. But it will work for you just to see if you can walk yourself through it mentally before we get to the code. And so that's the gist. That's kind of the big picture approach of how we're gonna do this thing. Couple intricacies in the code that we're going to deal with. So one thing we're gonna have to do is we're gonna have to start by saying, let's loop through A. I'll just call this A. So we're gonna have to say, all right, let's try all these letters. As we do that, we're going to have to keep some sort of cur list. I'm sorry, this freaking computer just lags so badly when I record. And we're also going to need to keep track of the index that we're at. So remember how we said after the first word we were at index 1, and then we were kind of at index, we had to look at all the letters in index 2 for all the words. We had 2 words, and then the first, or kind of all 3 of the letters at index 3, and so on and so forth. So we're going to be making recursive calls on these, and every time we make a call, we're going to have to do some sort of check to say, how do I find all of the words that have this prefix? So we're also going to need to have a method to find prefixes. The code is a bit long here, but the general idea I don't think is too complicated. It's going to follow exactly the template that we created. These are just a few points on what we're going to have to do within the code, but I think there's probably no better way to go through it than to actually start coding it with this methodology in mind. So let me know if you have any questions down below on what we've done so far. Review it again if you haven't, if it kind of didn't click the first time. But again, anything after that doesn't make sense, let me know, and I'm happy to address it. All right, so coding begins. Fun part. We don't need to do any error checking here in this case, because the way we're going to set this up will actually take into account whether or not there are any words given or not. What I will want to do though is I'm going to want to have some sort of result array, and let's kind of begin this way. So we said that to start things off, we would have to begin by working through every single word. So I'm going to have to make a call and saying, okay, can I start this thing with area? Can I start it with lead? Can I start it with wall? Can I start it with lady? Can I start it with ball? I'm going to walk through each one of these, and I'm going to call a recursive function on all of these, do all that backtracking magic, and store them into the result as I go, as I find results. And then after all that, I'm gonna return the result itself. So what we'll do is I'll say for word and words, we're going to have to call our function, and I'll just call it backtrack because I'm super creative. And in backtrack, we're gonna have to, we'll pass in a couple of variables. We'll talk about what those are. And once that's done, I'm just gonna return the result. So this is obviously just like a very small shell of what we're going to do in this main function. This backtrack function will have the bulk of the work. But when we call this backtrack function, we said we have to take into account a couple of items. We're going to have to keep some sort of current list of items that we have. So maybe we'll call that list, and we'll input word into it. So word being any one of these words, the word we're going to begin with every backtracking call. It'll be our first step. The other thing we're going to need is some sort of index. So we're going to start by looking at index 1. And the reason we're looking at index 1 is we said when I make my first call here, and that first call is going to be the word area, the next word I'm going to look for is one that has a prefix that is equal to all the letters at index 1. In this case, we have just one word, so it'll be 1. It'll have to begin with an R. So that's why I'm going to keep that prefix kind of passed in there. Technically, you don't need to. You have one word in here, so you can just say length of cur. Could kind of be used instead of index, but I think just to make it clear, I'll use index here. Now, that said, we actually have to create this this backtracking function. So I'll define backtrack. So say define backtrack. We'll use index and we'll use cur. All right. Now, what's our terminal condition going to be? If we've called this thing, let's say we had a one-by-one word. We wrote literally this word was just one character long, and so the length of current was equal to the length of any given word, kind of in words. Then we'll say the following. We'll say if the length of cur is equal to the length of I don't know. So any word that's going to be in cur. So if let me see here. Let's say cur of 0. It doesn't really matter. So every time we make a call, we're going to have something in cur. And if we had a 4-letter word in here, then cur of 0 would refer to the first item in that current, and that's 4. If the length of cur was 4, meaning we had 4 words in there, and each word had a length of 4, then we're done. Then we know that we can go to result, and we can say result.append cur, and we're going to have to change this in just a second. And we're going to return and say, okay, we're done. We're not returning any value here. We're just returning and saying our recursive call is done. A couple things we're going to need to do, since we're appending to this result here, and result is not local to this function, we're going to have to declare a non-local result, so it'll know to look in the outer function scope. The other thing we're going to need to do is, as we're making recursive calls with this list called current, if we make any changes to it, like pop off or append to it, that's actually if we append it like this to the result, then we're still pointing to that cur object itself, or the cur array, meaning any changes we make to it will be reflected in the result. We don't want that. I want to post like an entirely new list in the result that's not going to be modified. So I'll just put a new list called cur, and that'll be that. That's our terminal condition. Now, what are we going to want to do about the following? We're going to want to make some sort of recursive calls, and these recursive calls are going to have to be made on a certain prefix, right? So what is this prefix going to be? We're going to have to need some sort of prefix, and that prefix we said is going to be equal to all of the letters that are in this current list at a specific index. So when we had something like, let's see, what do we have here? Maybe I'll get rid of area because that's no good to us. We had something like ball, area, lead, and lady. All right. So we said that if we're at index 1, we have one item in there, then I'm going to want to grab that letter 1. If I have 2 words, I'm going to have to add every single character at index 2 from the 2 words, and so on and so forth. So what I could do is I can actually join the letters from all of these words in the following way. I now want to add word of index. Okay, so for each one of these words, I want to add the letter at the index, and we've passed that index in up here. And I want to do that for every word that's inside current. So for word in current. If, for instance, we have only these 2 items are in here, so ball and area, and my index is then going to be 2, well, I'm going to go to index 2, which is right here, and I'm going to take word of index, so word of 2, which is L, and then E, and I'm going to append each of those to this list. So word of index for every word in current. So what that would look like would be in an array that had an L and it had an E, and then when I join them, it's just going to be a string LE, right? So that's going to be my prefix. Now I'm going to have to find some sort of way to get all these prefixes. So we're going to write our own method for that. But we'll say maybe for candidate in get prefixes with the prefix. And what I'll do here is, maybe I'll So I'll make this a class function, and as I say this, I'm almost thinking maybe it would make a bit more sense to make this a class function as well, just to keep everything nice and clean, just for consistency, no other reason really. So I'm going to have to, and maybe I'll write this in a second. So let's presume we've written this function. I've got a function I can call where if I pass it a prefix, it will return all the words that contain this prefix. So in this case, it would return all the words that contained all the words that had LE as their prefix, for instance. That's what we'd be doing here. Each of these candidates we're going to want to try. So remember that whole throwing shit at the wall and seeing what sticks thing? We're going to have to try all of these candidates to see whether or not we can actually get to a word square with them. So what I can do is I can say cur.append this candidate. Now that we've appended it, we're going to want to try to see if we can add it on. The way we can add it on is by calling the backtrack function. So we can call self.backtrack, and we're going to want to call it with index +1 because we're now interested in the next letter over. So we're going to be grabbing not just the L and the E, but the L and the A and the D, right? We're looking one step further. And I'm going to pass in cur. My cur now contains the new candidate that I just put in. This backtracking, it's going to do its work. And whatever happens, may come to an end. It may find us a result, it may not. But once it's done, and we roll on back recursively, we're going to say, okay, cool, I've tried this word here. We've already tried this combination, so pop it back off. I'm done with it, right? We put it in, we try it, we take it out. And that's all backtracking is, right over here. Add it to current, try to do our work with current, and then take a step back and potentially try another one. If we get to the point where maybe we're here, there are no candidates. We try to call this and there are no candidates, like as if we if we tried to do, let's say we started with area. If we started with the word area, which we would here based on how we're making these calls, if we start with area, we jump in here, we haven't hit terminal condition, we check the prefix, and prefix is going to be an A. We try to find all the words with A, there are none. We never jump into here. And that's it. We back out of this for loop, nothing has changed. We go through the next word, lead. We try to go with lead. We come in here, the prefix we're going to need is E. Any words with E? No, there aren't any. Pop it back off, or not even pop it back off because we're not jumping into here. Try the next word in words, and that one would be wall. And then from there, we're going to make some magic happen because we're going to be looking for a prefix with A, and it's like, okay, nice, I found one. It's A, it's area. And then that whole example I walked through in the whiteboarding, that'll walk through here recursively. So this is all that we need to do for the actual backtracking. The part that I haven't written out yet is going to be, and I'm reading this here, and I don't think that I might actually go back and undo this because I'm trying to put into the result right here. So maybe what'll be easier, I'm sorry guys, this is a bit disorganized, but I'm gonna take one more stab at this, and I'm gonna keep this here. So I'm gonna keep this within this method. I think everything will be a tiny bit easier. Let me do that. And what I'll do is I'll just also create define get prefixes within this word square as well. And what we're going to need is the prefix. We already have access to words over here, so we're not really going to need to do anything much here. We may be recalculating prefixes multiple times, and so I think what would be pretty smart would be to have some sort of dictionary where we can keep our prefixes, and therefore we can say if we've kind of calculated one before, let's just return it. So if prefix is in prefixes already, then we're going to want to return prefixes at this certain prefix. Otherwise, it's not there, so we're going to have to build it up. And what we can do is the following: is we can say, since we've got no duplicate words, we don't need to use a set or anything. We can use an array. So I'm going to call this result, and it'll make it an array, and we're going to return the result when we get some words in there. But really what we're doing now is we're checking our entire initial words array, and we're seeing which of those words, if any, starts with the prefix. So what I'll say is for word in words, if word starts with the prefix that we've passed in, then we are going to say the following. Let's think here. We're going to say this. Prefixes at this certain prefix is going to equal a here. Let's do that. Prefixes of a certain prefix is going to start by being an empty array since we don't have anything there yet. So what we're going to do when we find a word that starts with prefix, we're going to say prefixes of prefix dot append word. And then we're going to return prefixes of prefix just like that. All right. So all that we're doing is we're saying if we've calculated this at any point, and I think here I need to use again non-local prefixes because we are going to be appending to it. But we're saying if I've calculated the words for this prefix before, just return them as it is. Give it to this function. Let it use them so we don't have to recalculate. Otherwise, let's calculate it from scratch. So we're going to say, we're going to start with saying there are no prefixes until we look through every single word and append any of them that do start with the prefix. And then finally, we're gonna return that list, and that list will go right here. That list presents a pile of candidates, either none or one or more, that we can try to build the rest of our square with. And I think that that's actually all that we need to do here. I'm gonna run this code real quick. I knew it wasn't gonna. Whoops, I forgot to erase the self here. So I was just saying I knew I wouldn't get it in the first try, but it was damn close, right? I think that was pretty impressive. So one caveat here, one little asterisk to this solution. As you can see, it takes a while, all right? But fear not, this isn't a bogus solution, I promise. The reason it takes a while is, well, I'm not actually entirely sure why. That's where I can kind of open it up to you guys. I will show you one solution that goes much faster, and it's in essence the same thing. It really is. So this will definitely give you more than passing marks in an interview. You don't have to worry about that. And that was the solution over here that ran in 404 milliseconds. I think the trick, is that we can pre-process some of these prefixes, or if not all of them, before we actually dive into doing all these backtracking calls. So it's a solution I had. The one that, and I believe I grabbed this one from the official solutions, I think. So I do want to show you guys that one just so you see it here yourselves. It's virtually identical. It really is. The only thing that I'm seeing is they call this build prefix hash table, which quite frankly I'm not sure why it's faster, because the way I'm understanding this is it builds every possible set of prefixes, not only the ones we're going to need. And that's what kind of confuses me about how this is so much faster. Maybe you honestly guys, if you know, let me know in the comments down below, because clearly there's some bit of optimization that I can do here. But even with that said, the exact same thing is happening. They're passing in an index and a current, and then sure the result, which they don't necessarily need to here. And they're just doing a backtrack call on every single one of these. The backtrack call is identical. It's the terminal condition. They're calculating the prefix. They're getting all the prefixes and then doing the exact same backtracking steps. So for what it's worth, if you don't believe me for anything, my solution's bogus because it took so long. You can see it here yourself. This took 10% of the time, and a bit more than that. And I'm not entirely sure what the major difference is in why it's taking that much longer. But nonetheless, this is still valid. I wasn't, I could have just kind of gone verbatim with this, but that wouldn't have been very honest with me because I don't know why it's much better at all. Nonetheless, like I said, this is still valid, so don't worry, you didn't waste your time watching this video. If you enjoyed it, if you liked it, drop a like, please. Comment, share, subscribe, the whole nine. Let me know what you want me to do next, and as always, I'll see you in the next video. Peace.